Europa may look frozen and lifeless, yet it could be hiding the largest ocean in the solar system. And the warmth keeping that ocean alive comes from a force stranger than sunlight. Tonight, on The Galaxy Scientist, we drift into the quiet physics, shaping Jupiter's icy moon, where tidal flexing warms the depths, cracks whisper of movement, and magnetic clues hint at water far below the ice. Some scientists believe conditions there could resemble Earth's earliest seas. If this gentle curiosity feels right to you, a soft like and quiet subscribe. Help others find calm. For now, settle in, and we'll drift toward Europa's hidden waters, unhurried and warm. In the icy shadow of Jupiter lies Europa, turning slowly through the dark. From far away, it looks almost simple, like a glass bead left out in the cold. A small world wrapped in a pale shell, its surface traced with long, faint scars and reddish-brown ridges that catch the light and shine even brighter than our own moon. There are no towering mountains, no gaping craters to break the smoothness, just broad, gentle plains of ice. It feels calm at first glance, almost still, as if nothing has happened there for a very long time. And yet that quiet mask is only the top layer. Beneath it, something is being carefully kept from view, like a secret tucked under a blanket of frost. Many astronomers have begun to wonder whether that secret might be one of the most important in the whole solar system. Over the years, spacecraft have drifted past Europa and stolen quick looks, each one adding a new piece to the picture. In the late 1970s, the Voyager missions sent back the first close images. Later, other flybys followed. Every time new photographs arrived on Earth, scientists found themselves staring at a face that refused to look old. Instead of being battered and pitted like our moon, Europa seemed strangely fresh. One Voyager scientist remembered looking at those images and being astonished by how flat the great expanses of ice appeared, like a single gigantic sheet pressed smooth. There were far fewer impact scars than expected, as though time itself had been wiped away. Something, or some process, was resurfacing Europa, quietly erasing the marks of ancient collisions. The ice did not look like a dead shell. It looked as though it had been moving, rearranging itself, answering to a hidden force deep within. That thought leads to a natural, almost irresistible question. Could there be an ocean hiding beneath the frozen crust? A buried sea stirring the ice from below. Instead of rushing ahead, it helps to linger with the surface itself. Europa's outer shell is anything but plain once you begin to look closely. It is etched with long, wandering cracks that wind across the globe, and tangled regions that look chaotic and broken. Dark, thread-like lines, some stretching over 1,000 miles, cross the pale face of the moon like fractures in a vast frozen lake. These lines, called lineae, sometimes run nearly parallel for great distances, and sometimes cross one another, weaving a delicate, global web. When scientists studied images from Voyager, and later from the Galileo spacecraft, something remarkable emerged. The opposite sides of certain cracks seemed to fit together like pieces of a torn photograph. If you slid one side back toward the other, the shapes matched. It was as if the icy crust had split apart, shifted sideways, and allowed darker material from below to seep up into the rift, staining the gap before it froze again. Great blocks of ice appeared to have broken loose and drifted into new positions, very much like the way sea ice can break, raft, and refreeze in Earth's polar oceans. The surface began to look less like a static shell and more like a frozen skin that had been tugged, cracked, healed, and tugged again. In some regions, the neat lines give way to something much more tangled. There are areas broad enough to cover entire cities or more, where the ice seems shattered and then clumsily repaired. Blocks stand askew, tilted and rotated, surrounded by lumpy, uneven ground and what looks like frozen slush that has been churned and left to solidify. Scientists, with a touch of poetry, call these places chaos terrain. The name fits. They resemble slabs of ice that were partly melted from underneath, allowed to float and jostle in soft, warm material, then frozen once more into a jumble of overlapping layers. These disordered icebergs, locked in place but clearly once adrift, whisper of something soft or even liquid that must have risen from below to disturb them. Elsewhere on Europa, the ice swells gently upward into domes, as though something has pushed from underneath, while nearby depressions and pits hint at places where ice has sagged or sunk. Taken together, these features paint a picture of a shell that is not rigid but active, slowly rising and falling over time, flexing over a hidden layer. It is hard to avoid the feeling that the crust is behaving almost like living tissue, responding to pressures and flows unseen. The natural question follows: what is making the ice behave as though it is alive? To find a clue, we can look back toward home. In Earth's Antarctic seas, broad plates of sea ice drift, collide, crack apart, and pile up in ridges as winds and currents move them around. The patterns can be strangely similar: broken flows, pressure ridges, rafts of ice that have overridden one another. On Europa, something analogous seems to be happening, but the engine is different. There are no fierce winds sweeping across open water, no salty waves rolling beneath. Instead, the driver appears to be deeper and slower, a push coming from the interior itself. Evidence of that hidden influence is scattered everywhere across Europa's face. The unusually smooth plains and the scarcity of long-lived craters suggest that some process is steadily renewing the surface, laying down fresh ice or rearranging old layers. One possibility is cryovolcanism, a kind of cold volcanism in which slushy water or icy mud seeps up from below, spills out and refreezes, smoothing and reworking the terrain. Another is the slow settling and shifting of an ice shell that is not stuck directly to solid rock, but instead floats on a layer of liquid. In the 1990s, as more data came in, many scientists began to feel that these clues were converging on a single extraordinary idea: an ocean beneath the ice. What began as speculation gradually grew into a serious, testable hypothesis. By the late 20th century, the notion of an internal ocean inside Europa was no longer just a dream. The Galileo spacecraft, launched by NASA and sent to orbit Jupiter in the 1990s, carried instruments perfectly suited to probing the moon's interior in subtle ways. Each time Galileo swooped past, it measured, listened, and watched. And with each flyby, the hints of a buried sea became harder to ignore. One of Galileo's tasks was to measure Europa's gravity, which reveals how mass is arranged inside. From these measurements, scientists could infer the moon's overall density and something called its moment of inertia, a quantity that tells how heavy the outer layers are compared with the deeper interior. The results fit beautifully with a simple structure: a thick outer shell made of water ice, resting above a denser, rocky core. That alone suggested a significant amount of water, frozen at the top, but possibly not frozen all the way down. Then Galileo found something even more telling in the invisible environment around Europa. Jupiter has a powerful magnetic field that sweeps through space like a vast, rotating umbrella. As the spacecraft flew through this region near Europa, the expected pattern of the field was disturbed. It was as though Europa itself were briefly growing its own magnetic response, twisting the field lines nearby. The best explanation was that currents were flowing in a large, electrically conductive layer beneath the surface. Given what we know about Europa's composition, the most likely candidate for such a conductor is a global ocean of salty water, wrapped around the rocky interior and hidden under the ice. Galileo's cameras and spectrometers added more quiet support to this picture. Certain patterns in the cracks and surface features only made sense if the outer shell of ice could move somewhat independently from the inner, solid parts. The longest fractures did not line up with the stresses that would appear if the crust were firmly locked to the rocky core. Instead, they matched the patterns you would expect if the crust could slip over a fluid layer beneath, shifting its orientation slightly over time. It was as though the icy skin had drifted, like a loose lid floating on a pot of slowly turning water. Two of Europa's largest impact scars showed another piece of the puzzle. Instead of being simple bowl-shaped craters, they displayed delicate rings inside rings, as though the shock waves from an impact had traveled through an upper shell and then echoed off something softer below. It looked less like rock being fractured and more like ice being tapped from the top while resting on a yielding cushion. All of these signs, taken together, pointed again and again toward the same conclusion. Beneath the cold shell of Europa lies a layer of liquid water, a hidden ocean circling the entire moon. But there is a lingering puzzle in that idea. Europa is far from the warmth of the sun, far beyond the region where surface water can remain liquid. How can a small moon, bathed in such weak sunlight, possibly keep an internal ocean from freezing into a solid block? The answer emerges when we watch how Europa dances with Jupiter and its neighboring moons. Europa lives in a gravitational tug-of-war, pulled not only by the giant planet, but also by the other large moons that share its orbiting family. As it circles Jupiter, Europa's path is not perfectly circular. Its slight oval orbit and the constant pull of its companions cause the moon to be stretched and relaxed over and over again. This repeated stretching and squeezing creates immense tidal forces inside Europa, much like the way Earth's oceans rise and fall under the pull of our own moon. But here the whole body is flexing. The crust and underlying layers are bent by many meters, roughly the height of a small building, every time Europa travels around Jupiter. That ceaseless flexing rubs the interior materials against one another, generating friction throughout the ice and rock. It is similar in spirit to kneading dough in your hands or rubbing your palms together on a cold day. Motion is turned into warmth. On Europa, this quiet, internal kneading goes on endlessly, orbit after orbit. That constant, gentle friction acts as a long-lived heater, a steady source of energy that keeps the hidden liquid from freezing solid. Jupiter's pull does more than guide Europa's path. It keeps the little moon warm from the inside out. In a way, the giant planet's gravity acts like a slow, patient furnace, flexing Europa over and over again until the very act of being stretched turns into heat. Calculations made by careful minds on Earth suggest that this tidal heating is more than enough to keep a deep global ocean in a liquid state beneath the outer shell of ice. That shell is thought to be many miles thick, perhaps on the order of roughly 9 to 15 miles. Cold and solid at the top, slowly softening with depth. Beneath it, the hidden ocean may plunge down for something like 60 miles, an enormous volume of water that could hold more than twice as much liquid as all of Earth's oceans combined. Because of all this, the idea that Europa hides a subsurface ocean is no longer considered a wild guess. Among planetary scientists, it has become a quiet, steady assumption. Europa is now often described as an ocean world, a member of a small and special family of bodies in our solar system, where liquid water is thought to exist in great abundance. In the simplest picture, the moon is layered, an icy crust at the top, floating on a salty sea, and beneath that, a rocky seabed, and, deeper still, a dense metallic core. It is not just a frozen marble, it is more like a world turned inside out, its most interesting part tucked away, where no sunlight can reach. That buried ocean does more than invite curiosity. Its presence hints at an entire realm of geology, and perhaps even biology, that could be unfolding in total darkness. Europa's ice is not a single, solid lid that froze long ago and never changed. It behaves more like a restless skin, a shifting, creaking cover that slides, cracks, and heals over the moving water beneath it, warmed slowly but relentlessly by Jupiter's pull. If a dark ocean lies under that crust, the next natural question is gentle but insistent. What kind of energy could sustain it, especially if anything alive is trying to make a home there? Sunlight, the familiar power source for life on Earth's surface, is almost completely shut out. The ice shell above Europa's ocean is miles thick, turning the world beneath into a place of perpetual night. No dawn breaks across its waves. No beams of starlight filter down through blue water the way they do in our own seas. Yet life, at least life, as we understand it, cannot simply exist on water alone. It needs a steady supply of energy, some difference it can exploit, some flow it can ride. On Earth, almost every ecosystem at the surface ultimately traces its energy back to the sun. Green plants and tiny algae capture sunlight, build sugars, and everything else feeds, directly or indirectly, on that stored light. But Earth holds a different kind of world too, far below the places where light can reach. Deep in our oceans, in trenches, and along long undersea mountain chains, there are communities that live in eternal darkness. Around hydrothermal vents on the sea floor, hot springs crack through the crust, and there, in the glow of no sun at all, quirky and almost alien-looking organisms gather. From these vents pours superheated water rich in dissolved minerals and chemicals. Tiny microbes cling to the rocks and to each other, using those chemicals as fuel, turning raw geologic energy into living tissue. Towering black smokers belch dark plumes into the cold water above, and around them cluster forests of tube worms, strange mollusks, and blind crabs that navigate by touch and chemical scent rather than sight. All of them are part of a food web built not on light, but on chemistry and heat from within the Earth. This discovery changed the way scientists think about where life can exist. If entire ecosystems can flourish without sunlight at Earth's seafloor, drawing their energy from the planet's inner fires, then perhaps Europa, with its buried ocean and warm interior, could host something similar. Planetary scientists now think this is not only possible, but quite plausible. Beneath Europa's ocean, there is almost certainly a rocky mantle and a central core. The same tidal forces that knead the ice shell also tug and flex the rock below, warming it and perhaps making it restless. If parts of Europa's seafloor are heated enough, water moving through cracks in the rock could be transformed, just as it is on Earth, into hydrothermal vent fluids. These could erupt or seep gently from the seabed, creating pockets where the surrounding water is warmer and richer in dissolved chemicals than the deep ocean around it. Along Earth's mid-ocean ridges, such vents dot the seafloor like tiny oases. On Europa, they could play a similar role, but in a far stranger sea. New computer models, built from physics and careful guesswork about Europa's interior, suggests that low-temperature hydrothermal vents could persist on the ocean floors of moons like this for billions of years. That long stretch of time matters. Even if Europa does not have a roaring volcanic heart, it may not need one. A quieter, gentler form of hydrothermal activity, driven by steady tidal warming rather than explosive eruptions, could still circulate water through hot rock and back into the ocean again and again. Over geological ages, such vent systems could provide not only warmth, but also a constant supply of dissolved minerals and chemical contrasts. In other words, they could offer the two things simple life needs most: energy and raw material. These vents would release fluids rich in hydrogen and other reactive substances. Where vent water mixes with colder, more oxidized ocean water, sharp chemical gradients arise. Microbes could, in principle, tap into those differences, using them as tiny batteries, drawing power by allowing reactions to proceed slowly through their own living machinery. Many scientists think that environments like this may have been among the cradles of life on early Earth, places where the first self-sustaining chemical networks took shape. If so, it is easy to imagine Europa's vents as distant cousins of those ancient nurseries, tucked out of sight under an alien sky. Unlike the most dramatic black smokers on Earth, which require intense volcanic heat and produce towering plumes, Europa might host more modest, warm vents. They would not be as visually impressive, but they could circulate far more water over very long periods, gently stirring the deep ocean and enriching it with fresh chemicals. On our own planet, such milder systems are believed to be widespread and stable, quietly cycling water through the crust and back again. The important point is that Europa's seafloor does not have to be a violent landscape of fire and molten rock. It could be a calmer, darker version of home, warmed enough to keep water moving and chemistry active. From there, the imagination cannot help but wander. In that pitch-black sea, beneath miles of ice, could there be tiny organisms drifting in the slow currents near warm vents, feeding on chemical energy and never knowing that above them lies a universe full of stars? The thought is both humbling and strangely comforting. But to move beyond daydreaming, scientists try to be methodical. When they look for life beyond Earth, they often return to a simple checklist, a short list of places where the conditions seem especially promising. For a long time, Mars held much of the spotlight. Ancient riverbeds and dried lake basins on its surface suggested that liquid water had once flowed there, and perhaps pooled in shallow seas. It felt like a neighbor with a faded but familiar past. Saturn's moon Titan also captured attention. With its thick atmosphere and lakes of liquid methane and ethane, a world that feels more like a chemistry experiment than a traditional planet. But Titan's surface is bitterly cold, and its strange liquids may be too alien for life that resembles anything we know. In recent years, quietly and steadily, attention has shifted more and more. When scientists talk about the most promising places to search for extraterrestrial life in our solar system, they circle back to Europa. The little moon seems to satisfy what some call the trifecta of habitability. It offers liquid water, useful energy, and the right chemistry. Each of these pieces matters. Together, they make Europa feel less like a distant ice ball and more like a hidden cousin to our own world. Water comes first. It is the universal solvent for life as we know it, the medium that allows molecules to meet, react, and organize into something more than the sum of their parts. Europa does not lack it. In fact, by many estimates, it is the wettest known world in the solar system. Beneath its crust lies an ocean that may hold roughly twice as much liquid water as all of Earth's oceans combined. Even though the entire moon is smaller than our own, it is strange to think that the greatest storehouse of liquid water in the solar system may not be on Earth, but hidden under ice, in a place bathed in perpetual twilight. Next comes energy, that quiet requirement that every living system must somehow meet. Europa's surface is nearly starless, shut away from the sun by its thick ice shell. But, as we have seen, the story beneath is more lively. Tidal heating provides a persistent source of internal warmth, enough to keep the ocean liquid and to drive possible hydrothermal circulation along the seafloor. Those vent systems could provide chemical energy, just as they do in Earth's deep oceans. And there is another, more surprising contribution. Jupiter's immense magnetic field and trapped radiation belts continually wash over Europa. High-energy particles slam into the moon's surface ice, breaking apart molecules and rearranging them. This process, called radiation chemistry, splits water and other compounds, creating oxidants such as molecular oxygen and hydrogen peroxide. These reactive substances accumulate in the upper layers of ice. Over time, some of them may slowly sink, either by gradual mixing or by being dragged downward when the ice shell is churned and resurfaced. If they reach the ocean, they could serve as food for microbes, providing the oxidizing side of the chemical balance that life can harvest. Estimates suggest that Europa's surface chemistry might produce on the order of about 1,000 tons of oxygen every day. That is a hard number to picture, but one way to think of it is this. If you could capture all that oxygen and deliver it to human lungs, it would be enough to support roughly 1 million people for a full day. For tiny microbes, which need far less, that represents an enormous potential reservoir of energy. The third piece of the habitability puzzle is chemistry itself. Life, at least in the form we know, is built from a familiar set of elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These must be present in some accessible form if life is to assemble and persist. Europa is thought to have formed with a share of these common ingredients. Over time, additional organic material likely rained down from space as comets and asteroids struck the surface, delivering complex carbon-bearing molecules forged in the cold between the stars. Studies of Europa's surface, using both space telescopes and instruments on passing spacecraft, suggest that its hidden ocean is probably salty and rich in dissolved minerals. Spectrometers, which can read the fingerprints of different substances from the way they reflect or absorb light, have detected compounds that hint at this chemistry. In some regions, the ice appears to contain ordinary table salt, sodium chloride, which may give parts of Europa's crust a faint yellowish tint. That in turn suggests that the underlying ocean could be similar in composition to Earth's seas, a briny mixture rather than a simple, pure water reservoir. More recently, the James Webb Space Telescope has added another piece to the story. It has detected carbon dioxide ice in geologically young regions on Europa's surface, places where the crust appears to have been disturbed or renewed not so long ago in cosmic terms. This is strong evidence that carbon from the hidden ocean is somehow making its way upward, reaching the surface before freezing in place. Taken together, these clues suggest that Europa possesses all the crucial ingredients for life's chemistry: abundant water, sources of energy, and a rich supply of carbon and other building blocks, all quietly gathered beneath a cold and silent skin of ice. When you set Europa beside its quiet rivals, its uniqueness becomes even clearer. Mars, for all its fame, is now mostly a frozen desert, a world where liquid water is rare and fleeting. clinging perhaps as thin films or salty trickles in special conditions. Saturn's tiny moon Enceladus hides a subsurface ocean too, and there we have even seen spectacular geysers spraying into space. Enceladus sits very high on the list of places where life might exist, but its ocean is smaller, wrapped inside a much tinier world. In such a compact environment, some scientists wonder whether there has been enough room and enough time for life to take root and diversify. Then there is Titan, Saturn's largest moon, wrapped in a dense orange haze. Beneath its crust may lie an internal water ocean, and on its surface rest lakes and seas of liquid hydrocarbons. Complex organic molecules drift and settle there like snow. It is a chemist's dream and a biologist's puzzle. Yet Titan's lakes are made of methane and ethane, chilled to temperatures so low that water is as hard as rock. For life that resembles life on Earth, those lakes might be too alien, too slow, and cold for familiar chemistry to dance. Two of Jupiter's other large moons, Ganymede and Callisto, likely hold deep global oceans as well. They may contain vast amounts of water, but their outer ice shells seem thicker, more rigid, and less active than Europa's. If the crust hardly moves, the exchange of nutrients and oxidants between the surface and the sea may be limited, like a pantry sealed and never restocked. A deep, quiet ocean beneath a thick, unchanging lid might be beautiful, but perhaps not as friendly to life that needs a constant flow of fresh ingredients. In comparison, Europa feels like a carefully tuned compromise. Its ocean appears to be both large and long-lived, sustained over billions of years by steady tidal heating. Its ice shows signs of cracking, shifting, and healing, hinting at cycles that could carry materials up and down between surface and sea. It has energy, water, and motion, all woven together. Little wonder that one of NASA's leading voices on the outer planets once said that if you had to pick a single place beyond Earth to look for living things right now, Europa would be at the very top of the list. In quiet scientific language, he noted that Europa seems to satisfy the conditions for habitability better than almost anywhere else in the solar system. So here we are, with a strong suspicion of a deep ocean, good reasons to think energy and nutrients are available, and a growing hope that something might inhabit that alien sea. Up to this point, most talk of life on Europa has been modest and careful. Researchers imagine microbes, simple organisms perhaps clinging to warm rocks near vents, or drifting as invisible clouds in the dark water. That alone would be astonishing. And yet, once the mind begins to wander, a more extravagant question slips in like a whisper. What if we are not the first intelligent beings to arise in this solar system? It is only a thought experiment, but an irresistible one. Europa's ocean may have been stable for an immense span of time, possibly longer than complex life has existed on Earth. Given so many orbits around Jupiter, so many cycles of heating and cooling, who can say how far evolution might have wandered in that hidden world? In a realm without daylight, eyes might never develop, or they might become exquisitely sensitive to the faintest glimmer. Creatures could instead learn to feel their surroundings through electric fields, or hear the world in pressure waves and subtle vibrations in the water. You can imagine complex beings, perhaps as graceful as fish or as clever as cephalopods, gliding through the blackness near warm vents, communicating with pulses of light or ripples of sound. In the most fanciful versions of this idea, they do more than survive. They build. They develop tools suited to water, structures anchored to the seafloor, networks of tunnels carved in ice from below. A whole society could, in principle, grow up under that icy canopy. thinking, and feeling in a world completely invisible to the open sky. If such a civilization existed, it might see Jupiter as a softly glowing disk shining through the ceiling, a pale lamp filtered by miles of ice and water. The stars would be legends at best, not points of light in any visible sky. Their universe would be the ocean itself, its currents, its vents, its occasional tremors. It is a haunting image, beautiful and deeply improbable, and it reminds us how little we truly know about the possible shapes life can take. Of course, imagination is not evidence. Until we actually sample Europa's environment, all such visions must remain gentle speculation. To move from wondering to knowing, we will one day have to draw closer to this moon, to study the places where the inside touches the outside, where the hidden ocean might briefly speak to space. In that sense, scientists often say that Europa's surface has to be read like a face, watched for any hint of breath. In recent years, Europa has begun to offer exactly that. Fleeting signs from beneath the ice, like sighs rising through the cracks. Astronomers turned the Hubble Space Telescope toward this small moon and were rewarded with a subtle but thrilling surprise. They detected faint plumes of vapor rising from near the surface, delicate columns barely visible against the darkness of space. In the year 2012, Hubble observed a soft ultraviolet glow around Europa's south polar region, a halo suggesting that molecules were being thrown upward and then torn apart into hydrogen and oxygen by Jupiter's radiation environment. One of the researchers leading that work, Lawrence Roth from the Southwest Research Institute in San Antonio, explained that the simplest and most natural explanation was that water vapor was erupting from plumes on Europa's surface. If that interpretation is correct, it would mean that Europa is only the second known moon, after Enceladus, to actively throw material from a subsurface ocean out into space. The idea that Europa might have its own breathing cracks, acting like geysers or icy volcanoes, stirred something electric in the scientific community. Suddenly, the ocean no longer felt entirely sealed. Hubble's observations suggest that these plumes are not constant fountains but intermittent events. They seem to appear and disappear, as though Europa is following a quiet rhythm. Interestingly, the plumes were detected when Europa was at its farthest point from Jupiter in its slightly oval orbit, rather than at its closest approach. This matches models in which the tidal stresses on the ice vary with position. When the moon is pulled and stretched the most, the fractures in its icy shell may open slightly, releasing pressure and allowing water vapor to escape. As Europa moves nearer again and the pattern of stresses changes, the cracks may pinch closed, silencing the vents for a while. In that way, Europa behaves almost like a living creature in slow motion, inhaling and exhaling on an orbital schedule. When the vents are open, the plumes are thought to rise for well over 100 miles above the surface, creating thin fans of water that quickly disperse and fall back as frost. Jupiter's gravity is strong enough that most of the ejected material does not escape into space forever. It returns, dusting the surrounding ice. To a distant observer, these sprays would be almost invisible. But to careful instruments and patient analysis, they stand out as unmistakable signatures of activity. Not long after Hubble's discovery, another piece of evidence emerged from an older source. In the year 2018, scientists went back to data collected decades earlier by NASA's Galileo spacecraft. They re-examined one particular close flyby from the year 1997, this time with fresh eyes and better models. During that brief encounter, lasting only a few minutes, Galileo's instruments had recorded abrupt changes in the local magnetic field and a spike in the number of charged particles around the spacecraft. At the time, The team did not have a clear explanation. With the benefit of later knowledge, those odd signals suddenly made sense. They matched what you would expect if Galileo had unknowingly flown through a thin cloud of ionized water vapor, the kind of environment produced by a plume erupting from Europa's surface. For roughly 3 minutes, the spacecraft appears to have passed through the outer reaches of a burst of material rising from below, sampling it without any intention to do so. This realization gave new weight to Hubble's results. Now there were 2 different lines of evidence: remote sensing from a space telescope and direct in situ measurements from a passing probe, both pointing toward the same conclusion. From time to time, Europa vents water into space. So what exactly are these plumes? You can picture them as narrow vents where fractures in the ice shell reach down toward pockets of liquid. In the southern polar regions, where stresses in the crust concentrate, cracks may open pathways to reservoirs of water or half-frozen slush beneath the surface. As pressure builds in these pockets, perhaps from warming, freezing, or tidal flexing, the trapped water finds the weakest point and forces its way up. When it breaks through to the surface, it flashes into vapor and fine ice particles, fanning out in a brief, ghostly spray above the moon before settling back down. This kind of activity is called cryogeology, or cryovolcanism. Volcanism, in which the erupting material is not molten rock, but water and other volatiles chilled to extreme cold. On Europa, it would be a frozen echo of volcanic eruptions on Earth, softer and quieter, but no less important. The discovery of likely plumes sent a thrill through those who dream of exploring this moon. A plume would not just be a pretty jet of ice. It would be a natural pipeline, carrying samples from the hidden ocean up into space where a passing spacecraft could gently fly through and taste them. A plume provides a direct channel from the hidden ocean to the surface. The thought of those plumes reaching up from Europa's surface naturally leads to a thrilling, almost unsettling question. What exactly is being carried in that ghostly spray? Is it only thin, cold vapor, or is there something more hidden in the mist? We know that the main ingredient is water vapor, breathed out from cracks in the ice. But if the plumes truly connect to the inner ocean, they might be lifting other things as well. Tiny pieces of Europa's deep world, scattered briefly into space before falling back like snow. We have seen something similar elsewhere. Around Saturn, the little moon Enceladus sends out its own geysers, jets of water laced with salts, organic compounds, and even microscopic grains that seem to come from the seafloor. From those grains, scientists have inferred hydrothermal activity and rich chemistry in the ocean below. If that can happen on a small icy moon there, it is natural to wonder whether Europa's plumes might also carry salts, organics, or other materials washed out of its buried sea. The Hubble Space Telescope, as powerful as it is, looks at Europa from very far away. Its instruments could detect the faint signature of water in the plumes, but they were not sensitive enough to pick apart a full recipe of complex molecules swirling in that thin vapor. All we can say with certainty from Hubble's data is that water is present, and still, many scientists quietly suspect that if we could pass a sensitive instrument through one of those plumes, if we could literally catch the breath of Europa in flight, we would find much more than just pure water. Perhaps the vapor contains tiny grains of salt or little flecks of clay, lifted from the ocean and frozen in an instant. Perhaps there are simple organic molecules, like small hydrocarbon chains or alcohols. In the most hopeful dreams, there might even be whole cells or fragments of cells. If any microbes exist in the ocean below, suddenly hurled upward as the water flashes into ice, The idea that Europa's plumes might be mixing chemical clues from the ocean into the space above is, by itself, a compelling reason to send new missions. These breathing cracks are, in effect, offering free samples from the inner ocean of a distant world. We do not need to drill through miles of ice to reach them. We only have to fly gently through the spray and collect what the moon is already giving away. If there are living organisms in Europa's ocean, even very simple ones, then the plumes could carry the faint fingerprints of their presence. Those fingerprints would likely not be tiny fish or visible creatures drifting in front of a camera. Instead, they might appear as specific patterns in the chemistry, certain molecules more abundant than they would be in a lifeless ocean. For instance, scientists often talk about unusual ratios of gases as potential signs of life, an unexpected excess of methane alongside hydrogen, for example, as has been observed in the plumes of Enceladus, and interpreted by some as a possible hint of microbial activity. At the very least, the detection of life's building blocks in Europa's plumes, simple organics, precursors to more complex molecules, would be an enormous clue. Even if those molecules were not produced by life, their presence would confirm that Europa's chemistry is rich and varied enough to support biology. To understand what we already know for certain, it helps to step back to the surface itself. Europa's ice is not just plain frozen water. It is dusted and stained with intriguing substances. The Galileo spacecraft, during its years at Jupiter, carried spectrometers that could analyze the light reflected from Europa's surface and tease out hints of its composition. Those instruments detected compounds such as sulfur dioxide, likely linked to sulfur dumped onto Europa from another moon, Io, which is violently volcanic. They also found hydrogen peroxide, a molecule that forms when ice is bombarded by energetic particles and radiation. And on top of that, Galileo's data revealed materials that did not behave like pure, clean ice at all. Their spectral fingerprints suggested the presence of salts or organic substances mixed into the frozen crust. Europa's trailing hemisphere, the side that most often faces backward along its orbit, and therefore takes the brunt of charged particles flowing through Jupiter's magnetic field, has a particularly striking look. It is marked with a mottled reddish-brown coloration, like stains on old snow. Scientists think that the mysterious molecules responsible for this color could be oxidized salts or complex organic compounds. Some may have originated in the ocean and been transported upward. Others may have formed when simpler substances on the surface were altered by radiation. Either way, the colors hint at chemistry that is more than just ice and rock. In the year 2023, the James Webb Space Telescope added a powerful new piece to this puzzle. Using its sensitive instruments, it detected carbon dioxide ice concentrated in a patch of chaotic terrain on Europa, a region where the surface looks recently disturbed and jumbled. The most compelling explanation is that this carbon dioxide comes from below, that it was carried upward from the churning subsurface ocean and then frozen in place. This does not prove life, but it clearly tells us that carbon, a necessary element for biology, is present in Europa's ocean and can make its way all the way to the surface. When we look for organic compounds specifically, we can again take guidance from Enceladus. There, NASA's Cassini spacecraft actually flew through the plumes and sampled them directly. Its instruments discovered a rich collection of organic substances, including relatively complex molecules, as well as molecular hydrogen, a sign of hydrothermal reactions between water and rock at the seafloor. Those discoveries painted a picture of an active, chemically rich ocean. We do not yet have the same level of detail for Europa. Our measurements so far are more distant and less precise. But if similar processes are taking place there, If warm rock is reacting with water, if vents are releasing hot fluids, then it would be reasonable to expect that Europa's plumes might also contain simple organics, such as methane, methanol, formaldehyde, or even amino acids, and other complex molecules frozen into tiny grains. One especially thrilling idea is that any microbes living in Europa's ocean could be swept up in the rising water that feeds a plume. As that water rushes into the frigid vacuum of space, it would freeze almost instantly, trapping whatever was inside into minuscule ice grains. Those grains would fall back to the surface, preserving their contents like tiny time capsules. In that way, the plumes could be scattering evidence of life if it exists across the icy crust, leaving it to be found later by a careful lander or a low-flying probe equipped to sniff and analyze the surface. Scientists also suspect that not all transport from the ocean to the surface happens through plumes alone. The local geology, especially in chaotic regions where the ice looks fractured and overturned, might be actively cycling ocean material upward. When new ice crust forms there, it could trap salts and organic molecules that were once dissolved in the water, then present them at or near the surface where they can be studied. If life in the ocean produces distinctive biochemical byproducts, certain fatty molecules, like lipids from cell membranes, for example, they might end up concentrated in those salty deposits as water freezes and leaves them behind. Recent studies suggest that some of these lipid molecules could survive the journey and remain detectable to instruments on a spacecraft, even after being exposed to harsh conditions. For now, though, the first hints of life on Europa remain purely hypothetical. We have not seen any direct sign of living organisms. What we have found instead are the conditions that make life possible: abundant water, active chemistry, sources of energy. We have evidence of intriguing substances like hydrogen peroxide and carbon dioxide, and probably common salt, all of which point toward an ocean that may, in some ways, resemble Earth's own salty seas, rather than a sterile, simple reservoir. These clues are enough to keep hope alive and to justify the effort and expense of sending missions to look more closely. Astrobiologists have begun to sketch out possible ecological scenes in their minds. Perhaps the warm rocks of Europa's seafloor are covered with microbial mats, thin layers of tiny organisms feeding on chemicals from hydrothermal vents. Slightly more complex creatures, analogues of brine shrimp or tube worms from Earth's deep oceans, might graze on those mats, drifting or clinging to mineral chimneys in the dark. These ideas are still only stories told with equations and models instead of ink, but they give shape to what we might one day find. The exciting part is that we may soon have a chance to test these ideas directly. Humanity has already built and launched its next emissaries to the realm of Jupiter, with the specific goal of exploring these icy ocean worlds up close. Two major missions are poised to make history by studying Europa and its neighbors in unprecedented detail: NASA's Europa Clipper and the European Space Agency's Jupiter Icy Moons Explorer, often called JUICE. Europa Clipper is the first mission dedicated entirely to Europa itself. Its robotic spacecraft has been designed from the beginning to answer a simple but profound question: could this moon support life? Launched from Earth on October 14, 2024, Clipper will spend several years crossing the cold, wide spaces between the planets before it settles into orbit around Jupiter, which is expected to happen around the start of the next decade. Rather than circling Europa directly, the spacecraft will orbit Jupiter and swoop past Europa many times, like a careful visitor making repeated, close inspections. Over the course of its mission, Europa Clipper is planned to execute about 50 close flybys of the Moon. During each pass, it will skim over different regions, gradually stitching together a detailed, global view of Europa's surface and interior. On some encounters, the spacecraft will travel only a few tens of miles above the ice, close enough that if plumes are active, it could fly through their faint spray and sample whatever the Moon is exhaling. To do all of this, Europa Clipper carries an impressive collection of 9 scientific instruments, the most advanced set ever sent to the outer solar system for studying an icy moon. Each instrument has its own role, like a different sense. Some will measure fields and particles, some will listen for changes in gravity, and others will look closely at the ice itself. Together, they are meant to map the structure of the shell, sense the hidden ocean, and analyze the chemistry of the surface and any material the Moon throws into space. High-resolution cameras, part of the Europa imaging system, will photograph ridges, fractures, and chaotic terrains with exceptional clarity, revealing features as small as a few yards across, and even allowing scientists to build 3-dimensional views of the landscape. Other instruments will peer beneath the surface, using radar to trace the thickness and layering of the ice, and a thermal imager will sweep its gaze over Europa's face, searching for subtle warm spots where the surface is slightly hotter than its surroundings, perhaps where water lies unusually close to the top, or where recent eruptions have left behind patches of gently warmed ice. An ultraviolet spectrograph on Europa Clipper will listen to light around the Moon, studying Europa's extremely thin atmosphere and any gases rising from plumes. By spreading that light into a spectrum, it can pick out the fingerprints of different elements and molecules, identifying what is there by the colors they imprint. In this way, it will tell whether the gas around Europa is only water vapor, or whether other ingredients are mixed into the breath of the Moon. Just as important are the instruments devoted to the ice itself. Europa Clipper carries a radar sounder called Reason, a device that will send radio waves down into the crust and then wait for the echoes to return. By measuring how long those echoes take and how they change as they bounce off different layers, scientists can begin to map the hidden structure of the ice shell. They hope to spot places where the ice may be warmer or more porous, and to detect pockets of briny water or small reservoirs tucked between the ice and the ocean below. If the ice is not too thick or chaotic, the radar may even glimpse the top of the ocean as a bright, smooth reflector many miles beneath the surface. A set of magnetometers, working with a plasma instrument, will carefully measure how Europa disturbs Jupiter's magnetic field as it moves through it. The Moon's internal ocean acts like an electrical conductor. As Jupiter's field sweeps past, it induces currents in that salty layer, and those currents create a magnetic response of their own. Tiny fluctuations in the readings, recorded over many flybys, will reveal how strong that response is. From this, scientists can infer how conductive the ocean is, which in turn tells them how salty it must be, and how deep the conductive layer lies beneath the ice. In this way, invisible lines of force become a kind of X-ray for the interior, confirming the ocean's presence and sketching its depth and character. Another experiment, often called the Gravity and Radio Science Investigation, will watch Europa Clipper with exquisite care. By tracking the spacecraft's radio signal as it flies past the Moon, scientists can detect tiny changes in speed and direction caused by subtle variations in Europa's gravity. Those variations reflect how mass is distributed inside the Moon, where the ice is thicker or thinner, and how dense the ocean and rocky interior might be. With enough flybys, a picture of Europa's internal layering can emerge, like feeling the weight of an object shift in your hand when something moves inside it. Europa Clipper is not only a set of eyes and ears, it is also a flying chemistry laboratory. On board is a mass spectrometer known as MassSpecs, designed to directly analyze particles and gases near the moon. Whenever the spacecraft passes through a plume, or a faint cloud of molecules kicked up from the surface by radiation, MassSpecs will scoop up these atoms and molecules and sort them by their mass. From this, it can determine what they are: water vapor, carbon dioxide, sulfur-bearing compounds, organic molecules, and more, if they are present. Alongside MassSpecs rides another sensitive instrument, the Surface Dust Analyzer, often shortened to SUDA. SUDA is built to capture tiny grains of ice and dust that have been ejected from Europa's surface, whether by plumes or by small impacts. Each microscopic grain that strikes the detector will vaporize in a tiny flash, revealing its composition in the pattern that follows. SUDA has a special talent for detecting salts and complex molecules trapped inside those grains. If a plume or a meteoroid impact sends a bit of ocean material into space, then SUDA and MassSpecs together can read its chemical recipe, telling us whether it is rich in sodium chloride, full of organics, or made of something we did not expect at all. In essence, Europa Clipper will let us take a cautious sip of Europa's ocean without having to drill through miles of ice. The stream of data it sends home will address several key questions. How thick is the ice shell? And is it still active today? Radar and imaging will show whether parts of the shell are partly melted, whether there are newly formed vents or fresh fractures where ocean water has recently pushed upward. Is the ocean truly global, wrapping around the moon? And what are its depth and salinity? Measurements from magnetometry and gravimetry will help answer that, tracing the outline of the conductive layer and estimating how much water it contains. What is the composition of the surface and any plumes? Spectrometers and particle analyzers will search for organic compounds, salts, and signs of hydrothermal chemistry, the chemical signatures of water interacting with hot rock. Are there places where ice and ocean are in especially close contact right now? Thermal and surface mapping may reveal regions of recent upwelling, warmer patches of ice, or chaotic terrains that sit above rising pockets of water. All of this will feed into the ultimate question, winding quietly beneath the others. Is Europa's ocean a habitable environment? Europa Clipper will not be able to look out the window and directly see a living organism. It is not designed to catch a microbe and declare it alive, but it will tell us how friendly or hostile Europa might be to life. It will measure the ingredients, the temperature, the energy sources, and perhaps even detect indirect hints, chemical imbalances that, on Earth, we would immediately suspect are linked to biology. From those clues, we can decide what kind of mission should follow. Across the Atlantic, another spacecraft is on its way to the Jovian system. The European Space Agency has launched the JUICE mission, short for Jupiter Icy Moons Explorer, a broad survey of Jupiter's frozen companions. Launched from Earth on April 14, 2023, the spacecraft began an 8-year journey through the inner solar system, using planetary flybys to gain speed. It is expected to arrive at Jupiter around the year 2031. Its main target is Ganymede, the largest moon in the solar system, where it will eventually settle into orbit. On its way, however, JUICE will make 2 close flybys of Europa. During these brief encounters, it will add its own perspective, complementing the work of Europa Clipper, even though it carries a different suite of instruments. JUICE's toolkit includes high-resolution cameras, spectrometers to study reflected light, a laser altimeter to measure surface heights, subsurface radar, magnetometers, and plasma sensors, 10 instruments in total. all tuned to understand Jupiter's moons and their environments. During its Europa flybys, JUICE will focus its cameras on selected regions, taking detailed images with resolutions down to just a few tens of yards. These views will allow scientists to examine new areas never seen before and to trace fine fractures, ridges, and pits. Its subsurface radar, called RIME, will probe the crust in a way similar to Europa Clipper's radar, but at a different frequency, which means it will be sensitive to different kinds of structures and may reach different depths. JUICE's spectrometers will analyze the composition of the surface, checking for the spectral fingerprints of salts, organics, and other compounds. Instruments devoted to studying particles and magnetic fields will investigate the space around Europa, confirming the presence of an induced magnetic field linked to an internal conductor and possibly detecting tiny plume particles or subtle changes in the surrounding plasma when the moon is active. Together, the two missions form a kind of duet. Europa Clipper, with its repeated close passes and specialized instruments, and JUICE, with its broader survey and different vantage points, will provide a multi-layered investigation of this ocean world. By the middle of the 2030s, we expect to have much new data, maps of the ice, measurements of the ocean's response to Jupiter's field, and direct samples of whatever material Europa releases into space. These missions are not the end of the story. If Europa Clipper finds compelling signs, for example, an ocean rich in organic chemistry, or patterns in the gases that look like possible biosignatures, the next move would be to send a lander designed to touch the ice. NASA has already outlined concepts for such a lander. A robotic explorer that could drill or melt a short distance into the crust, or scoop up fresh deposits laid down by plumes, then analyze them on the spot with sensitive instruments. Farther into the future, it is easy to imagine more daring machines. A probe that melts its way through the ice shell like a warm, glowing seed, lowering an instrument package into the ocean below, or even an autonomous underwater vehicle, an alien submarine roaming through Europa's abyss, listening and sampling in the dark. In the coming decade, Europa will cease to be just a distant, icy dot on star maps. It will become a place we know in detail, with named features and perhaps a catalog of the ingredients in its hidden sea. The great question of life beneath the ice will begin to shift from pure speculation toward evidence. We may discover simple organic matter frozen in surface grains, intricate but non-living chemistry hinting at possibilities, or even subtle signs that microbial life is shaping the composition of the ocean. It is also possible that Europa will surprise us in a harsher way, that its ocean turns out to be extremely salty, oxygen poor, or lacking in the right balance of ingredients, making it less welcoming to life than we had hoped. Either outcome would still be a profound discovery, teaching us more about how common or rare habitable oceans really are. The adventure of revealing the truth about this ocean world is only just beginning, and some of the most exciting discoveries may be waiting beneath the next crack in the ice.